In this clip, we'll do some reasonably horrible computations to show that if you permute the columns, like transpose two columns in a determinant, then the determinant changes sign. So we will dub this theorem 10.38. Oh, and I'm crooked. Okay, there we go. That's a little better. All right, so if the matrix B comes from the matrix A, by permuting columns, and we'll say the permutation of the columns is given by sigma, then the determinant of B is, oh, and I've run out of room. Then the determinant of B is the sine of sigma times the determinant of A. All right, so let's see. So for the proof of this guy, let's see. If, say, B comes just by swapping two rows, so we'll say by swapping the jth and kth columns, and we'll say let tau be the transposition that swaps j and k. Okay, so tau is a permutation, and it interchanges j and k and leaves everything else fixed. Okay, so then rho sigma equals tau for some permutation rho. Okay. So if we look at the determinant of B is, according to the formula, let's see, it's going to be the sum over all permutations, where we have the sign of the permutation times, and then we have B1 sigma 1 multiplied against, and we have the other columns chosen according to the permutation down to n sigma n. And then this will be the sum over tau rho in perm n, and we'll have sine of tau rho. So I'm just basically changing the dummy variable of summation here. So we have B1 tau rho 1 Bn tau, I'm doing sigmas instead of rows. Hold on a sec. Bam, bam. Rho, there we go. And then this is the same. Let's see, I can evaluate some of this now. So I've got tau rho and perm n, and then the sign of tau times rho is just minus the sign of rho, because we did one permutation. And then we've got A because B came from A by an application of tau. So we get this one. And so then we do the same trick that we did in the previous proof, which is that since we're summing over all the permutations, we can call them tau rho or rho inverse or whatever, because we're doing the sum over all of them, and it doesn't really matter what index we use. So I'll pull the minus sign out in front and just call it rho. And then this last thing that we have is the negative of the definition of the determinant of A, right? So that gets us one transposition. And then more generally, if sigma factors as T transpositions, then each one contributes a factor of -1. So the determinant of B is -1 to the T times determinant of A. And that -1 to the T, of course, that's the sine of sigma times determinant of A. The end. Okay, so that's the hairy part, but then we get an easy corollary. And that is that if A has two identical columns, then the determinant of A is equal to 0. And so let's see. So if we let, I'll come up with some stupid notation. Swap JK of A. Okay, so SWJK is the operator that swaps the jth and kth columns of A. So let this guy denote the matrix A with the jth and kth columns swapped. If these columns are identical, then what we have is the determinant of A is going to equal minus the determinant of the swapped guy, and this one comes by 10.3.8 that we just proved, and then this one is going to be minus det A, because we're assuming that the jth and kth columns are the same, and that means that the swapped one is actually the same as the original one. And we're done.